Hello everyone, in this video we are going to solve an example of first order system. So here a transfer function is given to us with a step function with an input of magnitude of b. We are going to use the final value theorem to determine the steady state response. We are going to find a complete response of the system. Also the part C is interesting. It wants us to find out how close do we get to the steady state value after the time that has passed is 1 time constant and also 4 time constant. How close are we going to be to the steady state value? Let's get into this. So remember, transfer function is output over input. So our transfer function is simply ys over us. So if we want to find the response or the output, or ys would be our transfer function times our input. So we have the value for transfer function is a tau s plus 1, and the input us is b, but in Laplace domain would be b over s. So if I want to solve part A, I know if I want to find a steady state response, yss, or in other words, limit of ys or yt when t goes to infinity would be equal to sys, but this time s goes to 0. So if I look at my function up there, if I just write it here, I just multiply by s. So I have a, b, and I have this s tau s plus 1. These two s would cancel out. If I plug in 0 here, would be 0. So I will have ab. So that's our steady state response of the system. But in addition to the steady state response, we want the complete response, which means that I need to look at my ys and try to simplify it so I can take an inverse Laplace. So it's AB is tau s plus 1. I can use fraction expansion to make it simpler with A and B. Therefore, finding A and B, I will have a tau plus b would be 0 because I don't have any coefficient of s in the numerator here. And also I have b or a would equals ab. So therefore b would be minus ab tau. If I plug in the value here, so ys would be ab over s minus ab tau, and I have tau s plus 1. Looking at the Laplace table, yt would be ab over s would be just a constant. And here I can simplify this, get rid of tau here, and it would be 1 over tau. So then that would be easier, it would be ab e minus t over tau. Or if I factor ab, would be 1 minus e minus t over tau. That's the response of our system. And if you want to check it, if t goes to infinity, you would find out that this component, the second term, would go away, and then we only have ab, which is a correct conclusion. Okay, sorry for that. Now we're going to calculate how close the system response is to the steady state value. Now part C is very easy. You're just plugging the value. The first one is t equals tau. So I'm going to plug in that value. I have yt. I'm going to put AB 1 minus E minus 1. That gives me value of 0.63 AB. And we know AB is the steady state response. So 63% of AB, or 60% of steady state response. And that's true all the time. Also t equals 4 tau. So yt would be AB 1 minus E 1/4. Sorry. Instead of t, I would write 4 tau, so that would be E minus 4. E to the power of minus 4. That would give me 0.98 AB, or 98% of a steady state response. Again, these conclusions are true for every system. At 1 time constant, you're going to get to 63% of a steady state. At 4 time constant, you're going to get up to 98%. So if I want to plot it, let's say this is yt, and this is time. The steady state would be AB, and my response is exponential. So let's say this is 63% of the response, so it will get there at 1 time constant, and we get up to 98% at 4 time constant. Let's write it 0.63 AB, and this part would be 0.98 AB. And depending on that time constant, you would see that it could take a short or long time. If time constant is only 1 second, so for 1 second, that would be in 4 seconds we get to 98% of our response.